All right. So the whole ton of you that are here today. Today we are homework number 8 should be turned in Google Classroom. We're going to go over the lab, and the report will be due a week from tomorrow. So you always have that week to do your lab report. And homework number 9 that you've been working on is due on Monday. Tomorrow we'll come here for attendance, and then we'll go over and do the lab, probably with a partner, especially if there's only 6 of you left. So, okay. So the rubric, this is also posted in Google Classroom, okay? And again, don't delete this when you turn in your lab report, because I have this set up so that I can type into it and it calculates your grade for me at the bottom so that I don't have to do that kind of math. Remember, it's been a while since you've done a lab report. So look back at the ones you did first trimester so that you don't make the same mistakes. Remember, the cover page is a separate page on the front that just has name, date, period, or title on it. Then the body of the report looks like a regular lab report, right? So you have your cover page, and then the rest of it kind of looks like a regular paper. But you're just going to have headings in there, so you're going to have purpose, and then you're going to have in a paragraph and complete sentences your purpose, and then you'll have your theory, and then in a paragraph or a couple paragraphs your theory and such, and it just kind of flows from page to page, okay? And again, you see here what has to be in each section. Your experimental, that might be steps, or like you can just summarize the procedure. Results, you have to have a data table. So, and you're going to have the one they provide with you, and you're going to have another one, or kind of combine them all in one. And then, again, you have your discussion and conclusion, and again, that's in complete sentences and in paragraph. What's new and what you haven't done before is the appendix. No matter where you end your discussion and conclusion, your appendix has to be a separate page. Okay? So appendix will be a separate page, and that may be handwritten. So I would just type the word appendix, and then you're going to hand write out those calculations. What I mean is I want an equation. I want you to show plugging in your numbers and units, and then the answer with the correct units and sig figs. And there's only one calculation for each of these, so that's going to be on your appendix. Right? Remember, page numbers are MLA formatting, right? So it's supposed to be your last name and the page number up in the upper right-hand corner, so forth, okay? Everybody kind of remember that formatting part of the lab report? And again, idea is when you are typing up your lab report, you should have this piece of paper or that grading rubric pulled up and be looking at it as you do your lab report. Because, again, it tells you what needs to be where, okay? Questions about the grading rubric? All right, going over then the lab that we are going to do tomorrow in class. Actually, I'm going to grab mine. So I'm going to have you guys read so that it's not all me. So my pet peeve on lab days is when people ask me what they're supposed to do, and it's all here on this. Plus, we're going over this because occasionally, if it's an area where I know that there are sometimes problems, I'm going to give you a clue about what to do, okay? So this is about calculating our empirical formula determination, and Bryn, you look like you're ready, so we read us the purpose.
To determine the empirical formula of magnesium oxide.
All right, the background, the first paragraph, please, Aiden.
Carbon dioxide, CO2, water, H2O, and ammonium, NH3, are just a few of many chemical compounds that you're familiar with. Have you ever seen a compound with a formula such as Na23Cl 3.9? Anyway, in fact, such a formula is impossible. Only whole atoms, not fractions of atoms, react with each other to form products. Also, although elements may react in different proportions to form more than one compound, the proportion of atoms in those compounds will always be a ratio of small whole numbers.
Natalie?
An empirical formula gives the simplest whole number ratio of the different atoms in a compound. For example, while the molecular formula for hydrogen peroxide is H2O2, the simplest whole number ratio of hydrogen and oxygen atoms can be expressed as HO. Thus, the empirical formula of hydrogen peroxide is HO.
Sarah?
In this lab, we will experimentally determine the empirical formula of magnesium oxide, the compound formed when magnesium metal reacts with oxygen.
So materials wise, yes, you'll have safety goggles that you'll have to wear. A crucible, little white dish. Okay. Crucible tongs are just like tongs. They look kind of like salad tongs, but they're tight at the end. A clay triangle. If you look at the next page, there's kind of a picture of what many of these things are in figure 9.2. The clay triangle is what the little pot that is a crucible is sitting on. Ring stand, ring support, balance, a gas burner, that's a Bunsen burner, 2 pieces of exposed film, and some magnesium ribbon. All right, that's safety first, please, Hannah.
In this lab, the first material will become quite hot and could cause severe burns handled improperly. Observe all precautions, especially the ones listed below. If you see a safety icon besides a step in the procedure, refer to the ones below for this meeting.
So that first one there, please, Scott.
Caution, wear your safety goggles. Do not look directly at burning magnesium. Do not inhale the smoke produced when the magnesium is burned.
So burning magnesium is because if you've ever seen people who are welding, okay, the sticks they use have magnesium in them. It's very bright, okay? And the smoke produced, so do we have anybody with asthma in here? Tomorrow, will you please have your inhaler with you and on you so that if the smoke that's produced bothers you, you don't have to like go find your inhaler, okay? Normally, and especially with just probably gonna just have 3 going, it's not too bad, but I would prefer that you just have your stuff with you, okay? Because we are gonna produce some smoke. All right, the next 2, Bryn.
Always handle the crucible and crucible lid with crucible tongs as shown in figure 9.
So they're just kind of showing you there how to kind of handle those. My suggestion is with that is practice before you start heating the crucible with like your hand underneath it so you can touch it if you're struggling and kind of find the best way or the most secure way to like pick that up and handle that. You need to be able to take the lid on and off, and you need to be able to take the crucible on and off the little clay triangle. So I would just suggest that you and your partner kind of practice that, decide which person's better at that, and just kind of practice before you get started, before the crucible gets hot. And that last one, please, Bryn.
Return or dispose all materials according to the instructions of your teacher.
All right, procedure. As you perform the experiment, record your data in data table 1. So if you take a look at data table 1. Right, so you're taking the mass of the empty crucible in the lid, and then you're gonna put the magnesium in it and take the mass again. And then when you're done with the reaction, you're gonna take the mass a 3rd time. I will tell you, you need to carefully read your triple beam balance. It should have, all of your readings should have 2 decimal places. If you don't, you may not get results, because you might find that the mass oftentimes does not change very significantly in this lab. It's definitely not the greatest lab in the world, okay? And so make sure when you do your readings that you read to at least 2 decimal places, okay? And you might remember you have to estimate that last one. Significant figures, you read everything you can for sure, and you estimate 1 more. All right, the steps of the procedure is step number 1, Aiden.
Set up the equipment as shown in figure 9.2. Clean a crucible and is covered with water. Dry them by heating in the hottest part of the flame for 5 minutes. Allow them to cool for at least 10 minutes. Measure and record the combined mass of the crucible and lid to the nearest 0.01 grams.
Okay, so there's that reminder, right, to read it to 2 decimal places. So again, they kind of have the setup here. One of the things that's not super clear though with your Bunsen burner, there's usually kind of two flames. There's a blue one, and then there's kind of the red or orange one. Which one is the hot flame? The blue. So you do need to kind of play with this. Now, one thing about the Bunsen burners that kind of I find entertaining every time is the barrel part gets hot, but the base part does not. So you can move your Bunsen burner in and out by touching the bottom of it, okay? You need to adjust it so that hello? Okay. 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 All right. Thank you. Bye. So you need to make sure that when you have this set up with your clay triangle, that the bottom of your crucible is sitting right at the top of that hot blue flame. So you may need to kind of a couple times like move it in and out your Bunsen burner to kind of get it at that right spot. Okay? So one thing about the Bunsen burner is once you have it lit, as long as one person stays at the lab station, don't turn your Bunsen burner on and off. They're sometimes not the easiest to get turned on and off. So just once it's lit, leave it on. And like I said, at the base, you can pull it in and out from underneath and kind of make your adjustments so that that crucible is sitting just right at kind of the very top of that hot blue flame. Okay? If you don't do that, it takes a really long time to catch your magnesium on fire. All right. The cooling part. I'd like you to allow them to cool for at least about 6 minutes. After about 6 minutes, because of how much time we have in class, and sometimes this takes a while to do, basically you need to have the crucible be comfortable for you to handle with your bare hand. Okay? So if we do 10 minutes each time, we should be okay. So if you want to go 10 minutes and then at 10 minutes you can just kind of handle it. But if it's like the time and you're watching the clock and we're starting to get close to the end of class and running out of time, then okay, you can let it kind of go 6 minutes, and if you can comfortably handle the crucible and move it to the balance, you're okay. The other trick to get your crucible to cool more quickly is to take it off of here and put it on the black surface, right? Because everything up here is hot, and it's going to continue to kind of radiate heat into this. Whereas if you can handle your crucible and set it on the lab station, right, that lab station is cool and it's going to cause the crucible to cool off more quickly. So you want to take your crucible kind of off of this setup when you're wanting it to cool. Does that make sense to everyone? Okay. Step number 2, Natalie.
Place a coil 25 centimeters length of magnesium ribbon in the crucible. Measure and record the combined mass of the crucible lid and magnesium.
Okay. So I'm going to give you a long piece. You're going to take this magnesium and kind of circle it up, coil it up so it's kind of tight. The bottom of the crucible is a little bit flat. Not quite that flat, but definitely a little bit flat. You want that coil in contact with the bottom of the crucible because that's the part of the crucible that's going to get really, really hot. If instead your coil's like up here along the edges, you may not be able to catch this on fire like you need to. So how tightly you coil this, you kind of want it to get to sit there in the bottom of that crucible. All right, the next one, please, Sarah.
Do not look directly at the burning magnesium. View the reaction through the pieces of film provided by the teacher. Over a high flame, heat the uncovered crucible on the triangle until the magnesium ignites. Do not inhale the smoke produced. When the magnesium begins to burn, immediately cover the crucible using tongs and remove the burner.
And people always forget to remove the burner. Okay? So basically, Once you have this sitting up here, you're waiting for this to light on fire. It should be pretty clear. This is usually pretty bright. So you'll kind of see light, or sometimes like, it's like almost like little sparkler. Like if you've ever had a sparkler, like those little sparkler sparks that come off of a sparkler, sometimes you kind of see some of that coming off that magnesium. So you really don't need to be like right over it looking inside of it, okay? You can kind of see from an angle, oh, yep, it's lit. You also are gonna have exposed film, and you can just kind of put that in front of your goggles. Sometimes people like stick it right in their goggles for the lab. And like I said, so that you are protecting your eyes. Yes, that should work. All right, number 4, Hannah.
After smoke production has ceased, replace the burner and continue heating the crucible. Caution, do not lean over the crucible. Remove the burner and carefully lift the lid and check the reaction every 2 to 3 minutes. After heating for a total of 10 minutes, check to see if the reaction is complete. The magnesium should be fully converted to a light gray powder, magnesium oxide. If ribbon-like material remains in the crucible, replace the burner and continue heating.
So this is one of the things where I want you to kind of make some comments. First off, right, we've caught it on fire, and we put the cover on the crucible and pulled out the Bunsen burner. It's easier to pull out the Bunsen burner, okay? There's smoke. Once we don't see any smoke, right, we put the Bunsen burner back and we continue heating it. But every 2 to 3 minutes, and you should time that 2 to 3 minutes, you're uncovering the crucible. Remember, we're trying to produce magnesium oxide, and this is magnesium ribbon. Why are we, besides checking the reaction, what's the other reason that we're taking the top off that crucible and replacing it every 2 to 3 minutes? What does the reaction need to burn? Oxygen. And it needs oxygen to produce the product, okay, what we're producing. So the part of the reason is, yes, to check it, but the other reason you're taking the top off is because you're allowing more oxygen to go in there. Most of the crucible lids fit like over the whole edge of the crucible, so they seal fairly well, okay? So by taking the top off the crucible, you're also replenishing the oxygen for that reaction to take place. So it is important that you kind of time it, okay? You guys all have your cell phones anyway. You can have your cell phone out tomorrow and like have a timer set for 2 minutes, just so that you kind of every 2 minutes you're taking that top off and checking it, okay? The other thing here, right, is 10 minutes converted to a light gray powder. So back up next to step number 3, would you make a note to observe carefully what the magnesium looks like before you burn it? Because I want you to think about like when you've been at a fire, like a bonfire, and you've had a log on the fire. The fire can go out, and does the log still have the shape that it did to begin with? Sometimes, right? And it's just kind of charred. Well, we've coiled up this magnesium pretty tightly. So a lot of times it's still gonna look like a tight coil. So how are you gonna tell if it's done reacting? Well, it's gonna look different. Usually this magnesium's kind of shiny, and sometimes it has a little bit of like black in it. When it's done, it's not gonna look the same. So part of how you're gonna tell, like it says it should be a light gray powder, but will you kind of make a note to yourself also? It should look different. If your magnesium looks different than it did when it began and you've heated it for 10 minutes, you're probably done, okay? Because you've coiled it up so tight, sometimes it doesn't like fall apart into a powder, right? It's not gonna be like a little pile of ash. It's probably still gonna be coiled up, okay? And just have kind of a different color or texture look to it. And when it does, you're done with your reaction, okay? Questions about that? All right, the next step, please. Are we on, Scott?
Turn off and remove the burner. Allow the crucible to cool completely for at least 10 minutes.
And again, I make a note there, I would encourage you to take the crucible off of here and put it down here. One of the things that sometimes does happen is sometimes the crucibles crack. Try really, really hard then to handle your crucible really carefully, because if it cracks, you're gonna have to use somebody else's data, because it gets hard to like take the mass anymore, okay? So sometimes they get like little cracks in them, and if you're really careful, you can like move it and not finish cracking it and finish your lab, and then we just throw the crucible away, okay? Number 6, Bryn.
Measure and record the combined mass of the crucible lid, and magnesium oxide.
Okay, so again, when that crucible's gotten comfortable to handle. Step number 7, please, Aiden.
Follow your teacher's instructions for proper disposal of the materials.
So I'm gonna tell you right now, right, the only thing you're gonna have is the magnesium oxide that you produced. You're just gonna kind of knock that out into the trash. Okay, and then you're gonna kind of wash out your crucible with some water and return it. Okay? So the whatever's left over at the end just goes in the trash. All right, so we see our data table, and we're gonna talk through some calculations with this, because usually the calculations for this people struggle with. So we're gonna call the empty crucible lid our A, the crucible lid and magnesium a B, and then the crucible lid and the combustion product C, because we're gonna talk through how to do all these calculations. Highly recommend that you write it down. So number 1, Aiden read last, so we're on Natalie.
Determine the mass of the magnesium used.
All right, so given that we have A, B, and C, how would we figure out the mass of magnesium used? How much magnesium we started with? Come on, somebody knows.
You just take the weight of B and then minus by A.
Yes, right? So for number 1, we're gonna take B minus A, and that gives us what we're gonna call number 1, our grams of magnesium used. All right, number 2, Sarah.
Determine the number of moles of magnesium used.
Okay, so we have grams of magnesium. Do you have a tool on your toolkit that converts grams to moles? I think you do. Anybody remember its name? Molar mass. Right, so you're gonna take your answer from number 1, right, and you're gonna use molar mass. Where will grams of magnesium have to be? Where will grams of magnesium have to be so they cross out? On the bottom, and the other unit in that tool is moles of magnesium, right? Right, so you're gonna take whatever this number was that you got here, right? The same number from here. Okay, that's what I mean by saying like number 1, it's your answer that you got, okay? Right, this is 1 mole. How do I get this number that goes here? Where do molar masses come from? Periodic table, right? So you're gonna look up the molar mass of magnesium on your periodic table. And then that's gonna give you, we're gonna call it number 2, the moles of magnesium that you used. All right, Hannah, when you're ready, number 3.
Determine the mass of magnesium oxide formed.
So again, that's gonna go back up to that data table. With the information we have in our data table, how are we gonna figure out the mass of the magnesium oxide, which is our combustion product? How are we gonna figure out the mass of our magnesium oxide that we formed? Do we wanna do C minus B? Is that gonna give me the mass of my product? Not quite. It's gonna be what? C minus A, yeah. So this would be C minus A equals our number 3, our grams of our compound that we formed. Scott, when you're ready.
Determine the mass of oxygen that combined with the magnesium.
So now we wanna know, right, here we have how much magnesium we had to start with. And remember, we can't lose or gain magnesium, right? And here we have how much of our compound we formed. So how will we figure out how much of that is oxygen?
Take number 1's answer and number 6.
Pardon?
Take number 2's answer and minus 1.
Not number 2, but
Number 3.
yes, number 3 minus number 1. So for number 4, we're gonna take our answer from number 3, which is our grams of our compound. We're gonna subtract our answer from number 1, which is our grams of magnesium that we used. And that's gonna give us our answer to number 4, which is our grams of oxygen that combined. Whenever you're done writing, Bryn, and ready, if you read us number 5.
Calculate the number of moles of oxygen atoms that were used.
So we have how many grams of oxygen. How are we going to figure out how many moles of oxygen that is? When we had grams over here and we need to figure out moles, what was the name of this tool we used? Molar mass, right? So we're going to use molar mass again, right? So we're going to start with our answer from number 4. Where will grams have to be? On the bottom. Right, and this is 1. This number comes from our mass on our periodic table for oxygen, which is I think like 15.99. And so that's going to give us our answer to number 5, which is our moles of oxygen we used.
Calculate the ratio between moles of magnesium used and moles of oxygen used. Express this ratio in the simplest whole number form.
So it's asking for a ratio of moles of magnesium to moles of oxygen, right? Our moles of magnesium and our moles of oxygen. Okay, and it doesn't matter too much so long as you know if I'm going to do magnesium to oxygen, then that would be my number 2 moles of magnesium I used over my number 5 moles of oxygen used. And the idea is that this should be a whole number. Now, remember I mentioned, right? This is for number 6. Remember I mentioned that this is definitely not the best lab in the world. Very rarely does this give you a nice whole number. So, I'm going to tell you a couple things. First off, there'll probably be a little fudging, if you will, here at this point, okay? But the first thing to try, if this doesn't give you a whole number, remember when we do the empirical formulas and we get moles of numbers and they're not whole numbers, we divide all of them by the smallest? First thing to try, whichever one of these is smaller, divide the other one by the smaller one and see if that gives you a whole number. And if that gets pretty close, like let's say you get 4.8 and 1. I'd call that 1 and 5 and call it good. Okay? If you get like towards a half, right? If that kind of happens and you get like 0.48, like 5.48, I might call that 5.5. And I might then like multiply that by 2 and make it 11 and make the other one 2. Okay? So this is where tomorrow, if you can, you and your partner, like if you're finished up, you want to see if you can do these calculations together so that you and your partner can have a conversation about this step number 6 and about how you want to try to get to a whole number. There is definitely some fudging involved typically in that step. Okay, and that's okay, because that's probably going to happen. All right, number 7. Win Mandy again.
Based on your 2 months data, write the empirical formula for magnesium chloride.
So let's say that this was magnesium to oxygen, that I had done it as a magnesium to oxygen ratio. All this is asking in step number 7 is if I figured out it was 2 and 11 in step number 6. In step number 7, I'm just going to write that as Mg2O11. There's no math involved in step number 7. It's just asking you to take this ratio of moles and write it as a chemical formula. All right, number 8.
Calculate the percent error in your determination of the magnesium oxygen mole ratio using the accepted value provided by your teacher.
Your teacher's me, so I'm not going to give you the accepted value. Here's what I'm going to tell you. To get the accepted value, you need to write the chemical formula for magnesium oxide, which you've been able to do since chapter 6. Right? So I'm not going to give that to you. You're going to write the chemical formula for magnesium oxide, right? And it's an ionic compound, so you're going to do symbols, charges, crisscross, lowest whole number ratio, right? And that's your chemical formula. Now, let's say when you do that your formula ends up as Mg2O5. That's not right, but I'm just saying if, for example, that was your accepted value. The question people often have then is, how do I do that calculation for number 8? So given the numbers that I kind of have up here on the board, here's what number 8 would look like, right? This is my experimental value, 2 to 11. Here's my accepted value, 2 to 5. It's just important that I have, if I have magnesium on the top here, then I have magnesium on the top of this fraction here. Okay? Does everybody understand where the 2 over 11 versus 2 over 5 came? So, how do I do this for this one? Then my equation would be percent error equals my accepted value, 2 over 5, minus my experimental 2 over 11, the absolute value of that, divided by my accepted, which was 2 over 5 times 100. So to do that calculation, you're going to take whatever those ratio is and kind of make it a fractional number. And all of you, I think, probably know how to do that on your calculators, right? You can use some parentheses if you want, or you can just change it into a decimal, right? Do 2 divided by 5, whatever that decimal is, okay? And do it. But either way, you're going to do your percent error calculation. Number 9. Sarah? Or you already read?
Yeah, we're on.
Hannah. All right.
Identify major sources of error in this experiment. Explain how the magnesium or oxygen ratio will be affected by each error you identify.
Right? How many sources of error am I going to want? 3, right? 3 sources of error. That's always what I ask for in lab report. Again, remember, it's not admitting you made a mistake. It's looking at spots where people could make mistakes, right? A big one for this one would be if somebody doesn't know how to read the triple beam balance. That's going to be a source of error, right? Maybe somebody didn't take the lid off, right? So they didn't get the right amount of oxygen, right? So you're just looking at the whole procedure as you do it and like, oh, like somebody could make a mistake there, or the crucible cracked, right? And they lost their whole product. Okay, so there's lots of things that you can put for there. Number 10, Scott.
Is there agreement among the results obtained by others in the class? What does the class data tell you about the empirical formula of the compound?
So here's what I'd like, right? We're gonna do this lab Friday. Monday, when you come to class, I'll give you a couple minutes at the start of class to kind of check with your partner if you didn't get through number 7 up above, and agree on what your empirical formula is, and we'll put it on the board. And then you'll kind of write that down and then kind of use that data to answer that question. That data doesn't have to be in your lab report, okay? And there's one more question on the back, Bryn.
Interpret in terms of atoms and in terms of moles the subscripts in a chemical formula such as C2H6.
Right, so atoms, that's pretty easy, right? Because how many carbon atoms is that? How many carbon atoms is that? 2. How many hydrogen atoms is that? 6, right? But remember, that's also moles. That's part of what we talked about in this chapter. So the other way we can interpret that is 2 moles of carbon atoms and 6 moles of hydrogen atoms. So there's no math required to answer question 11. It's just interpreting it that both ways. All right, I want to come back for just a moment to your grading rubric because this is a spot where people always make mistakes. Down under results, it says data table 1, and then it says results of all the calculations in your data table. Right, here's my data table 1. Okay, whatever your numbers are for that. That's pretty easy. People don't usually have a problem with that. Where they have a problem is the results of the calculations in the data table. So after you've done all these calculations, you're going to create your own data table, and it is going to say mass of magnesium used, and then whatever your answer to number 1 was. And then in step 2, you did moles, so you're going to have moles of magnesium used, and just your number. These calculations are your appendix. Okay? But the data table is where, as a scientist, we just look really quickly to look at your data. So you're going to have each one of these calculations like labeled. Like this one is the mass of my compound formed. And then my number that I got for number 3. Okay, so there's going to be 1, 2, 3, 4, 5. You really probably don't need 6 in there. And 7. Right, so there'll be 6 of those things kind of here in this data table. And again, it's just a title of what that is, and then that number, the answer you got at the end with the correct number of sig figs. The work, this work goes in your appendix. Okay, but this data table needs to go in your results section. And oftentimes people kind of forget to do that, and it's worth quite a few points if I want to say. Right, that's 10 points. Okay, and it should be a pretty easy 10 points.
She said all of them except for number 6.
Yeah, you really probably don't need, or not number 6, sorry. You really don't need number 7 in there. You should have this number 8 though. Like the bottom one should be your percent error and whatever percentage you got. So any of them that you kind of have numbers for, like 7 you don't really have a number for, but the rest of them you have a number. And you should kind of have those numbers. Questions about this lab? So what can you do the rest of class today? Well, you have a homework assignment that's due today, so if that's not done, you can finish that up. You have homework number 9 that you're working on that's due on Monday. Also remember, you can actually start to do some of your lab report before you actually do the lab. So you could probably do your purpose and your theory before you even do the lab if you want to get started on it. Okay? Any questions? Hopefully there's a few more of you here tomorrow.
I think Hannah